Welcome back to part 2 of the water cycle. We'll start off this video discussing runoff versus infiltration, and then we'll talk about how precipitation and evaporation is very different depending on what latitude you're located. And then we'll continue talking about global change in water, which is a topic that's on everyone's mind these days. And then we'll finish off discussing where water is located on the Earth's surface and subsurface. Let's return to the precipitation part of the water cycle. What happens to water as it hits the Earth's surface? Well, that depends on what surface the rain hits. If rain hits saturated or impervious ground, it begins to flow overland, downhill. This is called runoff. Runoff is enhanced when the soil is either saturated with water from previous rain or if the ground is impervious, such as a parking lot or a building. So surface runoff is the water that's most easily accessible for human use. It takes very little effort to obtain it. You don't even have to drill for it. You just need to pond it by a dam and a reservoir. Globally, this accounts for about 1/3 of all precipitation, while the other 2/3 either evaporates, transpires, or soaks into the ground, and that's called infiltration. Water that infiltrates into the ground percolates down until it hits an impermeable barrier. And then the water will fill the pore space within a rock, a sediment layer, and that's called an aquifer. And the water can get stored there as groundwater that can then be tapped into later. So urban areas that have a lot of man-made impermeable surfaces such as sidewalks, streets, buildings, parking lots have high runoff, about 80% of runoff and only about 20% of infiltration, which kind of makes sense. But in more rural areas where there's a lot of vegetation and soil, there's only about 20% runoff and the remaining 80% infiltrates into the ground to become groundwater. And we're seeing an increase in flooding due to increased urbanization, and that's because runoff is becoming greater and infiltration is becoming reduced. As streams flow downhill as a result of runoff, it merges with other streams, eventually creating a channel. When this happens, the smaller of the two merging streams is known as a tributary. Many tributaries will collect and dump into a larger or a trunk stream. So it's this branching network of streams that's known as the drainage system or the drainage network, and it collects water from a broad area, and that area is called a drainage basin or a catchment or watershed. They all mean the same thing. It's the area that drains into a major river. And this drainage basin is bound by a topographic ridge or a topographic high, and that's called the drainage divide. So precipitation that falls on different sides of the drainage divide will enter a totally different drainage system. So if you look at a map of North America and its drainage divides, you'll see that the land surface is divided very unequally. So the continental divide is what separates drainage networks that terminate either into the Pacific or the Atlantic. So most of the water that falls in the U.S. drains into the Gulf of Mexico and then joins the Atlantic. So it's only a small portion of North America that drains into the Pacific Ocean. And the Mississippi River has the world's 4th largest watershed. It's found in 32 states in the United States and 2 Canadian provinces, and that all empties into the Gulf of Mexico. About 40% of the landmass of the continental United States is covered by this watershed. That's incredible. We've talked a bit about the phase changes that occur as part of the water cycle, but not really about what it takes to bring about the changes and how these changes affect the surrounding area where they occur. Ultimately, it's the sun's energy that drives the most important phase change in the water cycle, evaporation. Evaporation in turn affects local weather patterns and the Earth's overall climate and energy budget. So let's take a look at that for a second. Saying the sun drives the water cycle is a bit of an oversimplification. It's a bit more complicated than that. Many of the global circulation patterns, and therefore weather patterns, are the result of the sun differentially heating the Earth. Solar heating of the Earth's surface is uneven. Solar warming is generally greater at the equator where the sun shines more directly overhead, and much less at the polar regions where the sun is low in the sky. At the equator, the sun's rays strike the Earth almost perpendicular to its surface, warming up just a small area. At higher latitudes, the curvature of the Earth causes the rays to strike a larger surface area, so the same amount of heat is distributed over a larger area. This means the sun does not warm up the higher latitude regions as much as it does at the equator. And this differential heating is passed on to the air above, causing changes in atmospheric pressure. And ultimately, wind and weather patterns which affect the water cycle are derived from this differential heating. Warmer air temperatures at the equator then creates an area of a rising air mass due to increased temperatures, which promote cloudy skies, which then increase precipitation along that equatorial band. So yes, on a global scale, the amount of water evaporating is about the same as the water delivered to Earth as precipitation, but it does vary geographically. As you can see in this map that shows mean annual precipitation rate, notice it's highest along the equator. And this rainy band moves to the north and south throughout the year, depending on seasons, but in general hovers near latitude 0. It's not a coincidence that this is also the location of the world's remaining rainforests. Since at the equatorial region there's a rising air mass associated with this increased precipitation, it's not surprising that the higher latitudes between about 15 and 35 degrees latitude, both north and south, are associated with descending dry air masses and therefore the world's deserts, such as the Sahara in Africa, the Negev Desert in the Middle East, and the Gobi Desert in Asia. But if you look at the location of the world's desert, you'll notice a few that don't follow this pattern, especially the ones that trend north-south as opposed to east-west. These deserts are located on the leeward side of mountain ranges. So when warm, moist air hits this topographic barrier called a mountain range, the air mass gets pushed up into the atmosphere where it cools and will hit the dew point and then either rains or snows and dumps its moisture on the windward side of that range. And then when the air mass goes up and over the mountain range, it's a drier air mass and has less moisture and doesn't rain or snow on the leeward side. But if we go back to the maps of precipitation and evaporation and combine them, we get a map that looks like this that shows where evaporation or precipitation dominates. As I mentioned, precipitation dominates at the equator and evaporates at bands near about 30 degrees north and south, the Tropic of Capricorn and the Tropic of Cancer. Not only is this trend important for understanding why the world's deserts are located where they are, but it helps explain why most of the Earth's latitudes are inhabitable by humans. The phase changes of evaporation and precipitation bring about a temperature change as well. Evaporation requires the input of energy and thereby cools the surrounding area. You know that because sweat cools your skin and therefore your body. And precipitation, on the other hand, releases energy. So heat moderation is accomplished through this phase change. So evaporation removes heat from the tropics and releases it at the poles or at the higher latitudes through precipitation, because condensation releases heat. So this is a way that heat is carried from the sun-warm equatorial regions to the higher latitudes. And this phase change is a major part of the Earth's energy budget and has a big impact on evening out the climates across the globe. Let's look a bit closer to precipitation patterns within the continental U.S. Clearly, latitude is not the only determination of precipitation rates. Even across one latitude, there are widely varying precipitation rates. And if you look at this map, one of the most obvious trends is that precipitation is greatest near the ocean, which makes sense since they are the largest source of moisture and the air has to travel over many topographic barriers to get to the interior regions, so it has dumped most of its water by then, resulting in lesser precipitation. Now, if you zoom into California in particular, we'll see there's incredible diversity in terms of its climate zones and the amount of water that the state gets. It has a lot to do with the topography of the state. The amount of precipitation can vary as much as 60 inches a year within 100 miles. Areas of California that are deserts and certain areas that get 100 inches a year of rain. Up until now, we've mostly been talking about how the water cycle affects climate by moving energy around the globe. But climate, and in particular warmer temperatures, is affecting the water cycle. Global warming is speeding up the water cycle and affecting precipitation rates, evapotranspiration rates, groundwater recharge, snow melt, runoff, among others. As we mentioned before, with the warmer climate, evaporation rates will increase. So what does that mean? Well, it means two things. For areas that have high precipitation rates, this means more water vapor in the atmosphere, which means wetter atmosphere, more and heavier floods. For drier areas, this increase in evaporation means a 20 to 30% reduction in runoff or snowmelt. And so these dry areas will become more water stressed. So global warming means you'll get more of what you have. Wetter regions will become wetter and prone to flooding. Drier regions will become drier and more prone to droughts. This is particularly alarming in areas with declining availability of fresh water for great parts of the world. For 14 years, NASA has been collecting incredibly detailed gravity measurements using satellite. The mission was called GRACE, and it measured the very tiny space-time variation in the Earth's gravity field. So it's effectively weighing changes in water mass over large river basins and groundwater aquifers. In summary, it quantified the rates at which all regions on the Earth are gaining or losing water. And here's the main takeaway from that study that ended in 2020. The world's high latitude regions, including the northern part of the United States, as well as the global tropics, the low latitudes, those areas are getting wetter. And secondly, simultaneously, the mid-latitudes, the arid to semi-arid belt sandwiched in between, are getting drier. So this pattern of wet getting wetter and drier getting water has long been predicted, but this study confirms these projections. And it also goes on to say by 2025, half of the world will be water stressed. That means over half of the world's major aquifers are past sustainability tipping points, meaning that the rate at which groundwater is being withdrawn are far greater than the rates at which it's being replenished. As I mentioned earlier, there's an immense amount of water on Earth. It's just that only a small portion of the Earth's water supply is fresh. Furthermore, it's not evenly distributed across the globe. So here's where water is stored on Earth. Keep in mind that this water cycle describes the movement of Earth's water, so realize that a chart like this is just a single point in time. And only about 2.5% of the Earth's water is fresh. And most of the fresh water is locked up as glaciers in Antarctica and in Greenland and as groundwater. So there's very little water that's actually on the Earth's surface as streams and rivers. So the takeaway from this is that most of the Earth's water is not directly useful to people because it's salty or inaccessible. In addition to the widely varying size of the water reservoirs, the amount of time water spends in each reservoir is hugely varied. This is called its residence time. And the larger stores take longer to turn over and have longer residence times, such as the oceans, about 1,500 years, while the smaller reservoirs turn over faster and have much shorter residence times, like the atmosphere or rivers. Thanks for joining me on this amazing journey that water takes as it cycles through all the nooks and crannies of the Earth, sometimes becoming a part of us, the oceans, the atmosphere, and even rocks.